You think the great climate disasters of the 19th century are Tambora in 1815 and Krakatoa in 1883. They're in your textbook. Everybody knows them. You're wrong. Between Tambora and Krakatoa, there is another disaster. It killed millions. It turned the sun blue. And for 194 years, nobody knew what volcano did it. Until last year, August 1831. Picardy, France, a wheat farmer named Jean Marchand walks into his fields at noon. The wheat should be golden. It is gray. He looks up. The sun, which should be a bright yellow disk, is the color of a deep sapphire. Indigo blue. He has never seen this before. Nobody has. In Hamburg, the same week, the German Weather Service notes the sun is, quote, violet at midday, end quote. In London, the Times prints a small column about a strange blue luminary in the heavens. A sailor off the coast of Massachusetts records a green sun. From Cairo to St. Petersburg, the same observation. Something is wrong with the sky. In each village, the local priest says the same thing. God is angry. The summer is over. It is 15 degrees Celsius in July. Bonfires are lit in August. Rain falls for 40 consecutive days in some regions. The wheat dies. The potatoes rot in the ground. By autumn, food prices in Paris triple. Across the Mediterranean, in southern Italy, an entire island appears in the sea. A small volcanic island called Ferdinandea, and disappears within months. Many people think it is the cause. It is not. 8,000 kilometers away, in northern India, the monsoon fails. The wheat harvest collapses. The cotton harvest collapses. 200,000 people will die in a famine. The British East India Company will struggle to record. 12,000 kilometers away, in Edo, Japan, the rice harvest of 1832 fails. Then 1833. Then 1834. The Tenpo Famine begins. By the time it ends in 1837, between 500,000 and 1.5 million Japanese will be dead, and nobody on Earth knows why the sun was blue. For 194 years, scientists tried to identify the volcano. In the 1850s, it was Babuyan Claro in the Philippines. The timing matched. The chemistry didn't. In the 1890s, after Krakatoa, scientists looked at Bardabunga in Iceland. Wrong sulfur signature. In the 1960s, El Chicon in Mexico. Too small. Ferdinandea, the appearing island in Sicily. Too local, too low. Each generation thought it knew the answer. Each generation was wrong. The problem was the search itself. Volcanology in the 19th century was looking for a known volcano. But what if the volcano that killed millions was not on any map? What if it was on a remote island where no human had ever lived to write down what they saw? To find that volcano, scientists would need a witness who never blinked. Something that had been recording the sky since 1831 and was still recording in 2025. That witness, it turns out, was Greenland. Joseph McConnell runs the Ultra Trace Chemistry Laboratory at the Desert Research Institute in Reno, Nevada. You may have heard the name. He's the same scientist whose team identified the Roman lead pollution that lowered Roman children's IQ by 2 to 3 points across the empire. That was 2024. He published it in PNAS, the Proceedings of the National Academy of Sciences. In January 2025, he published another paper in PNAS. This one was about 1831. His team analyzed 3 Greenland ice cores, one called NEAM 2011, S1, one called Tunu 2013, one called B19. Each ice core is a long cylinder of frozen Arctic atmosphere. Each layer is a year. Each year traps the chemistry of that year forever. The Ultra Trace Chemistry Laboratory at DRI can detect elements at parts per quadrillion. That's like detecting a single human hair in 100 Olympic swimming pools. It is the most sensitive volcanic forensic technique ever invented. McConnell's team looked at the layer for 1831. They found a sulfur spike consistent with a magnitude 5 to 6 volcanic eruption. They found particles of volcanic glass. The chemistry of those particles told them where the volcano had been. It was not Iceland. It was not the Philippines. It was not Sicily. It was, they had to look this up, a remote island in the Kuril chain between Japan and Russia in the western Pacific, an island called Simushir. On Simushir, there is a volcano called Zavaritskii, named after a 20th century Russian geologist. Before 2025, almost no volcanologist had heard of it. Zavaritskii had erupted in the summer of 1831 with the force of approximately Pinatubo in 1991, releasing 13 teragrams of sulfur into the stratosphere. The sulfur scattered sunlight, turned the sun blue, and cooled the Northern Hemisphere by approximately 1 degree Celsius. The mystery was solved. So what is Simushir? It is a 30-kilometer-long island in the Kuril archipelago. It is currently uninhabited. It is administered by Russia, claimed in part by Japan. It is part of a territorial dispute that has lasted since World War II, but until the 18th century, Simushir had people on it. The original inhabitants were the Ainu, an indigenous people of Hokkaido, Sakhalin, and the Kurils. They called the island Simushir, meaning, quote, big island, end quote. They had been there for at least 1,000 years. They fished the surrounding waters. They knew the volcanoes. They probably had a name for the mountain that would later be called Zavaritskii, but by 1831, they were gone. Russian and Japanese expansion in the 18th century had displaced them. Some moved to Hokkaido, some moved north. By the time the volcano erupted, no human being lived on Simushir to witness it. This is the irony at the heart of the story. The largest volcanic eruption of the 19th century, not associated with Tambora or Krakatoa, happened on an island that humanity had emptied of human witnesses just decades earlier. The mountain blew its top, with no one there to record the event. The sulfur drifted into the stratosphere. It circled the planet. It turned the sky blue from Hamburg to New York. It killed 200,000 in India and 1.5 million in Japan. It darkened skies for 2 years, and the mountain itself stood empty. The caldera lake filled with rain. Volcanic mist rose for decades. The Ainu displaced, died of disease and starvation in their new homes. The mountain that had killed them, and millions of others, sat quietly on its empty island, waiting for someone to find it. It would be 194 years. Why did it take so long? The answer is geography, politics, and luck. Geographically, Simushir is one of the most remote places on Earth not buried in ice. It is roughly equidistant between Sapporo and Petropavlovsk-Kamchatsky. There are no commercial flights, no ports, no reliable weather stations. The only people who go there are scientific expeditions, and very few. Politically, from 1855 onward, Simushir has been claimed by both Russia and Japan in various combinations. After 1945, it became Soviet, then Russian. Western volcanologists could not easily access it. Soviet volcanologists studied closer, more accessible volcanoes. The mountain, that would become known as Zavaritskii, was named after a Soviet geologist in the 20th century, but it was never well studied until ice core science came along. The Greenland ice cores have been drilled since the 1960s. The chemistry of preserved atmospheric samples has been refined since the 1990s. The level of resolution needed to fingerprint individual volcanic eruptions, to say, this signature, with this sulfur isotope ratio, with this trace metal pattern, came from this specific location, is something McConnell's lab pioneered in the 2010s. In other words, The technology to solve 1831 only existed for about 10 years before they actually solved it. This is what science looks like in real time. A question can be asked in 1831 and remain unanswered until 2025. Not because nobody cared, but because the tools to answer it took 2 centuries to be invented. Here is something that I want to leave with you. In the summer of 1831, while Zavaritskii's sulfur was drifting through the stratosphere and the Northern Hemisphere was watching the sky go blue, a 22-year-old British man was walking up the gangplank of a small survey ship called HMS Beagle. His name was Charles Darwin. He boarded on December 27, 1831. The volcano had already erupted. The sun was already blue. Famine was already starting in Bengal. Darwin sailed for 5 years. The journey would lead him to the Galapagos. The Galapagos would lead him to the theory of evolution. 2 stories from the same year. One mountain on an empty island in the western Pacific killed 1 million Japanese, 250,000 Indians, and an unknown number of Europeans, and we wouldn't know its name for 194 years. One ship in the Southern Hemisphere carried a young man whose ideas would reshape biology, and his name would be on every textbook within his lifetime. History remembers some events fast. It buries others for centuries. The world was always like this, and it still is. So what does this mean for us? In 2026, 2 things. First, right now, around the planet, there are between 1,500 and 2,000 active volcanoes. About 100 of them are well monitored. In Japan, Iceland, the United States, Italy. The others are not. Many are in remote locations like Simushir. Many are underwater. The Hunga Tonga eruption in 2022, the largest of the 21st century so far, happened underwater near an island chain we do not closely watch. If a Zavaritskii scale eruption happened today, we might know about it within a week. But we might not, and we definitely would not be ready for the consequences. A 1 degree Celsius cooling spread across the Northern Hemisphere would not just be a curiosity. It would be a global agricultural catastrophe at a time when food systems are already stressed by climate change. Second, the story of 1831 is the story of a question that took 5 generations of scientists to answer. 200,000 died in India. 1.5 million died in Japan. We are only now beginning to understand why. We are only now beginning to give those deaths a cause. This is not a satisfying story. The dead do not come back because we found the volcano. Their families' suffering was real and is over. The mountain on the empty island is, in some sense, an answer that arrived too late. But it is also a reminder there are still events on Earth, in deep oceans, on uninhabited islands, in the cores of polar ice, that we have not yet found the names for. There are explanations we have not earned yet. There are deaths we have not yet given a cause. The job of a civilization is to keep asking questions that took 200 years to develop the tools for. To keep building the laboratories that can detect a part per quadrillion. To keep drilling the ice cores that record what no human ever saw. The reason we know about Zavaritskii now is that someone, somewhere, was patient. Someone in 1960 thought, maybe Greenland's ice can tell us things about the past. Someone in 1990 refined the chemistry. Someone in 2010 built the lab at DRI. Someone in 2024 noticed the unidentified spike in 1831. Someone in 2025 wrote the paper. A 200-year answer is a long answer. But the only way to get it is to keep asking. Joseph McConnell is not done. In a laboratory in Reno, his team is examining another ice core layer. The year is 540 AD. The Northern Hemisphere is about to enter a decade-long cold period that historians call the Late Antique Little Ice Age. Crops will fail across Europe and Asia for 10 years. The Eastern Roman Empire will be decimated by a plague that kills perhaps 1/3 of its population. This is the worst climate event of the last 2,000 years. And the volcano that caused it, nobody knows. Yet, that is the next story.